Hello everyone. Today is the day 4 of 75 hard research challenge and I'm going to talk about what I did on day 3, right? So in day 3 what we did is that I studied something called positional embedding, and what happens is that in the case of transformers what we have is that we have a sequence of words with us, and in this sequence of words what we do is that if we simply give this particular sequence of word as input to the transformer, these are treated as something called bag of words. That means that there is no ordering in this. That would imply that if I have a sentence like this, need to force order among words, and if I reverse the sentence saying that words among order force to needed, they would be both treated equally. So otherwise what we have to do is that we have to add positional embedding. That signifies that what particular word is at what position. For example, needed is at first position, to is at second, and so on and so forth, right? So what we do is that in the original paper of Attention is All You Need by Vaswani et al., what they did is that they used something called additive sinusoidal positional embeddings. So what is additive and what is sinusoidal positional embedding? So let's first focus on what is additive. So additive simply means that if you have a word needed, or rather a token needed, so you have a token at Ci, the value of the Ci is added with the position embedding of Pi, right? So essentially what we are saying is that before you apply the transformer on top of it, TFM, I am denoting the transformer with this, you have to first apply the add the positional embedding to the corresponding token embeddings, right? Okay. So now we will focus on what is sinusoidal embedding. So sinusoidal embedding is essentially, it uses this particular formula that position, or rather let's focus on this particular vector here. So at each position pt we will add a d cross 1 vector, right? For the position at pt, right? So what it says is that it will be in terms of pairs like this. It will always be even. That means that d percent 2 is equal to 0, right? Always. I mean, that's what people usually do, and it does not hurt us in any way. So what they say is that first dimension of this positional vector would be sine of omega 1 t, second would be cos of omega 1 t, third would be omega 2 t, and fourth will be omega 2 cos omega 2 t, right? Okay, so what is omega k? Omega k is simply 1 by 10,000 raised to power 2 k by d, where k is the exact number. For example, in this case k is equal to 1, k is equal to 1, again k is equal to 2, and k is equal to 2 is equal to, and so on and so forth. So if we have a d dimensional vector here, k is equal to d by 2 at the last in the last two positions. Okay, so this is exactly what we are doing, but why do we do this? Why don't we do something else? And where did this sine and cos like values come into picture, and why is this a good positional embedding? So to gain some intuition on top of it, I was reading some blog here. You can access the blog from here. I'll add the link in the description also, but let me briefly give you the intuition on this. It says that let's say we have to use binary encoding. So how would we go about it? Is that at position 0, 1, 2 and so on, we will have a binary encoding of this. For example, at the position 0 we will have all zeros, position 1 we can have 3 zeros and followed by 1, then we have 00, 10 and so on and so forth, right? Now let's make some observations here. The last bit, which is the least significant bit, varies every other number. That means 0, 1, 0, 1, 0, 1 and so on, right? You might have noticed it in any preliminary class on computer science also. For the second, it varies twice in the period, right? That means it goes 0, 0, 1, 1, 0, 0, 1, 1 and so on and so forth. Similarly, the most significant bit varies by the value of 8. That means first you get 8 zeros, then you get 8 ones, right? So based on that, let's say we want to use this binary encoding. It would be beneficial to use it, but it will be totally waste of space, in the sense that because these d-dimensional vectors are continuous in nature, so to have a binary value here of 0 or 0, 0 or like 1, let's say at position t is equal to 0, you will have all 0 vector, right? At position 1 you will have 0 0 0 0 and 1, right, and so on and so forth. But the problem with that is that this is total waste of time, because this can be floating values and you are forcing them to be binary. So what would you do? You will have a close approximation to, let's say, 1 and 0, and what would that be? And that can be a continuous like function like sine or cos function, right? So that's what they are doing here essentially, that first bit is changing for the tth position in a particular fashion, and second bit is again changing in a particular fashion, and so on and so forth. So let's visualize this in a particular graph that is shown here from the paper. On the x-axis we vary the k. That implies that this particular thing is getting varied here. Okay. So essentially this vector is now represented as a line in this particular graph, right? And this is the time. That means P naught is here, P1 is here, P and so on, and P50 they have plotted, right? So let me zoom in a little bit. Okay. So this is P naught, then P10, P20 and so on. So this is the positional embedding used in P naught, this is the positional embedding used in P1 and so on, and this is the positional embedding used in P50. Okay. So what does that mean? That here you can see that the least significant bit, that is this, is varying very frequently, right? But the most significant bit or the dimension in this case is not varying very frequently. This is similar to what we saw in this case, in the case of binary embeddings also, where the least significant bit was varying very frequently, but the most significant bit was not varying that well, that frequently, right? So, so you can get some sort of intuition on top of it, that okay, so I am creating this positional embeddings that are varying based on the time step as well as the depth of the d-dimensional vector that we are using, right? Okay, so now this blog post made a very interesting thing and very interesting discovery. I would highly recommend you reading the original blog here. It says that why do we add the positional embeddings and not concat it? Probably at that time, when the paper came, the number of parameters were not supposed to be kept that high, and because the GPU space was limited as compared to what we have today, so probably it was done to save some space in the form of number of parameters, right? Okay. There's another Reddit post that I saw that was linked from this particular blog post, and it led me to a very interesting analysis by someone else also on the Reddit. So what do? We have this formulation. Let's analyze this formulation with and without the additive positional encodings. Okay. Let's say we do not have the positional embedding with us. Then what happens? Then what happens is that we have the formulation that Q K transpose, which is normalized by dk, is then multiplied by the value after taking the softmax. So original value with additive positional embeddings will be something of this sort, that you have a query matrix and you have a key matrix also. This should ideally be k. Right, let me just correct it. So this should be k. You have a query matrix and you have a key matrix, and you multiply x with query and y with query. This is for the when you use x as query and y as key for a particular value in the qk transpose matrix. So this will be a transpose. This will be a matrix of size n cross n, correct, where n is the sequence length, and this is this is representing one element of one element of the this particular matrix. Okay. So now what happens with positional embedding is this. Let's say we add positional embedding P1 for x and P2 for y. So this is the equation that we will have, right? And based on this equation, I am just expanding this equation, that we have WQX, right, plus right WQP1. Similarly, I like moved this inside. Then I expanded it by a multiplication rule, simple like that, and this is what we get. So what does it mean? It means that attention between x as query and y as position, because you have x as query and y as the key, right? Okay, so this should again ideally be, apologies, I'm correcting myself here, this should be key. Okay, so x as query, y as key, so attention between these two. Then what is the attention score when you use x as query but the positional embedding as the key, right? So you are not attending to the like the word embedding or the token embedding, rather the positional embedding. And similarly, what happens when you use the position as the query but the exact token value or key for the token, right? And similarly, what happens when you simply attend on the two positions p1 and p2 as key, query and key respectively, right? Right. So it seems that we also compute attention between key, query, position, and position with position, right? So all four combination are being used here. Okay. This is what I studied in the last, that means yesterday. So I'm going to stop here and I'm going to continue this positional embedding chapter tomorrow in another video about what I studied today. I have already completed it, but I'm not going to share it today.